So, lesson 5, mixed resistor circuits. Mixed resistor circuits, they have some series parts and some parallel parts, which seems pretty obvious. That's what we mean by mixed. To solve, okay, you need to be able to identify which parts are in series, which parts are in parallel. Simplify the circuit to find the total equivalent resistance, and I usually call that RT for R total. Find total current. So ideally, we're going to simplify the circuit to one voltage source, where this is voltage total, and one mathematically equivalent resistor, where this is resistance total. And then you can find I total, which is going to be V total divided by R total. And once you have I total, Ryan, I've said a few times, if you have total current, the question's going to fall apart. Then start using Kirchhoff's laws. Okay? So our strategy is, first of all, make sure you can tell the difference between series and parallel. Simplify it in its simplest form. You may redraw the circuit, or you may just write the R total somewhere. Find total current, use Kirchhoff's laws. It says identify resistors in series or parallel. Let's call this R1, R2, R3. Which ones are in parallel with each other? Okay, so if I wanted to find the parallel equivalent, if I wanted to find 1 over R, and my abbreviation for parallel resistor, I pull out what we did way back when with forces. My abbreviation for parallel is 2 lines. Would be 1 over R2 and 1 over R3. What would the total resistance be then? It would be R1 plus whatever you found the parallel equivalent to be. Because, Sanj, what you've just done is you've replaced this with one single resistor, so that mathematically you can now say this is like having just one resistor there and these guys not being there at all. Oh, now R1 is in series with the new mathematical R parallel. You just add them up. And it'll become easier with numbers, but we're walking through the abstract stuff. In terms of series, in terms of parallel, these guys here would be in series. You could replace that with one mathematical equivalent, and that one mathematical equivalent would be in parallel with this guy. And then you could go further than that too. Here, got a couple in parallel, a couple in parallel. You know what? These are complicated enough that we're going to start going to numbers, to actual values, Sanj. I think it's going to become clearer. So let's move to the next page. Oh, one more yucky one here. Those two are in series. You could combine those two and then combine these in parallel. And then once you combine those in parallel, it would be in series with this one. You can combine it. Example 2. Find all voltages and currents and draw a summary diagram. Draw your simplest possible circuit. Okay. It says find all voltages and currents. First thing I'd look for is total current. Did this circuit tell me total current anywhere? Nope. Then I look for any resistor where there's 2 pieces of information. Did they tell me 2 things there? No. 2 things there? No. 2 things there? No. You know what? Now my strategy is going to be rewrite this mathematically. First thing I want to go look for are any parallel resistors. Any that are in parallel.
Yeah.
What? Okay, so I'm going to replace this. I'm going to replace this with 1 over R parallel equals 1 over 10 plus 1 over 15. On your calculator, what is R parallel? Remember we said you could use that fancy, wonderful, handy-dandy reciprocal button? 1 divided by 10 plus 1 divided by 15. Reciprocal. I find that a 10 and a 15 in parallel is the same as 1 6-ohm resistor. So mathematically, I can say this. This is the same as a 4-ohm and a 6-ohm. Right, Sanj? 1 over 10, 1 divided by 10 plus 1 divided by 15 equals reciprocal. Reciprocal? Don't do that. Or you forgot where it is? Show them. Suggest someone hasn't done the homework. Oh, sorry. Now, why is this so nice? Okay, hang on. I got to pause and get this done. Why is this so nice? Because the 4 and the 6, I think someone said, I think Doug, you said they're in series. So you know what? Mathematically, what's our total? Mathematically, what's our total? Hang on here. Sorry, what's our total? 10. I could redraw that second circuit, but I got the total resistance. So, oh, and what's V total? Here's the key now. What's I total? I total is going to be V over R, right? I equals V. It's the equation you have on your formula sheet, Jordan, right, is V equals I times R. I'm assuming we're at the stage where a 3-variable equation we can rewrite in our sleep. Oh, and you know what? Although it doesn't say total, yeah, total current should be total voltage over total resistance. Hey, I can do that in my head. Jordan, in your head, 20 over 10. The total current, and I'll go to 2 sig figs just to be paranoid, is that. Now, why is that so handy? Now, I'm going to walk back to my original circuit, and right where the end of the battery is, right in the positive part of the battery, what I've called the chairlift, I'm going to say right here I have 2 amps. Let's go skiing. How many amps are in this first resistor? Sorry, you're right. Must be 2, because there's no junctions. Why is that so handy? Do I now know 2 things? Then I know 4 things, although I've stopped asking you to find power. You could find power. More specific, I can tell you the voltage drop in that resistor. What's the voltage drop in this resistor here? In your head. 8. I times R. Why is that so helpful? How high was the chairlift? How big is our voltage source? What did we lose here? Can I get to the bottom of the ski hill going down that run? Can I go like this and get to the bottom? Then how high must this 10 ohm resist? How many volts must we lose going through this 10 ohm resistor? Must use 12. Do I know 2 things? I know 3 things. What's the current in that particular resistor? It's going to be V over R, right? 12 divided by 10. Really? 12 divided by 10? 1.2. Really, calculator people? 1? Oh, I weep. I weep. 1.2 amps. What was total current? What was total current? 2. So if 1.2 amps went this way, how many amps went this way? Do I know 2 things? I know 3. Wait, you know what, though? Wait. I don't need to go I times R to tell you the voltage. Were we able to shake hands, split up, and meet up back here? Then these 2 resistors must have the same voltage drop. If the left-hand one was 12 volts, I'll bet you this one is 12 volts. I'll bet you if you go 0.8 times 15, I bet you the answer is 12, which it is. And congratulations, we have solved this circuit. This is the kind of question that you'll have on your test. On the multiple choice, I'll probably give you the total current. On the written, this is good stuff. How would I mark this? I would look for you showing me some type of work. Oh, what was our parallel? It was 6 ohms. I forgot to write it here. I would look for probably, I would say, I would give you 1 mark if I saw, if there's a 7-mark question, 1 mark if I saw that, 1 mark if I saw that, 1 mark if I saw that, and then probably 1, lots of ways to give out the 1 marks and label everything. Let's try another one. Example 3 says, yep. Were you asking for Kayvon and taking one for him, or was he asking for you? Okay. Mm-hmm. We believe you, Mr. Calculator Boy. I'm more inclined to believe the guy that brought his calculator. Just saying. Example 3. Find all voltages and current. It's solve the circuit. Okay. Did they tell me total current anywhere? Did they tell me any resistor with 2? If I knew that, this would fall apart. Okay, I'm going to have to rewrite this, getting the equivalent resistance. Suggestions. Joel, get your down. We got the annoying buzz. Thank you. Suggestions. Oh, by the way, a number of you got emails from me on the weekend. You've lost your studies. I'll be talking to you later on in class. We'll even put little appointments on your phones to remind you when you're in my classroom during your study block. It's going to be fun. Yeah. Use those phones for something positive. Okay, we have, don't write this down. I'm really going to muck up this diagram. These 3 are in series. See them? A 12, a 6, and a 2. What's that the same as? That's the same as 118. So what I'm going to do right now is I'm going to do a quick rough sketch. 20, thank you. Where I have this 6 ohm. By the way, my rough sketches, I tend to put the resistor right in there, partly because I have trouble doing the zigzaggy thing, partly because it really emphasizes to me which ones are in series and which ones are in parallel. That's wrong, but it's just something I've developed over the years drawing them like this. So I have a 5 going this way, and this is the same as, what'd you say, Andrew? Right now, that's what we have. You okay with where that 20 came from, Kayvon? Yeah. Now what? Which ones? The 5 and the 20. So now I can say 1 over R parallel is going to be 1 over 5 plus 1 over 20. By the way, before I even crunch the numbers, Doug, look up. What's the smallest resistor in this parallel component? 5. I'm telling you, the answer is going to be less than 5. It always is when you're doing parallels. Will this work out evenly? I don't know. 1 divided by 5 plus 1 divided by 20. Oh, this one will. They often won't. It's really awkward to make these work out nice. Our parallel is 4 ohms. 4 ohms, you okay with that? So now what I'm saying is this. This circuit is the same as 30 volts, 6 ohms, 4 ohms. That's mathematically equivalent to this big monstrosity here. Why is that so nice? What is it? What is our total, Kayvon? Yes. What is V total, Kayvon? And I know that total current is going to be total voltage divided by total resistance. Hey, Kayvon, in your head, what's the total current? 3. Nice. Again, my friend who creates these is very good at making these work out nice. I long since stopped trying to. You will sometimes have decimals. Do I now know total current, Logan? Now I go back to my original circuit, and I always start at the top of the battery, right here, and I say, hey, that's 3 amps. Why is that so handy? Let's ski. First resistor, do I know anything new about this first 6 ohm resistor? 3 amps. And because I know the amperage, what else do I know? The voltage drop, which is, I lose 18 volts. Now, why is that so helpful? I don't know. Why is that so helpful? Oh, so you're saying that's a legitimate ski run right there? So my chairlift, my battery, my source was 30 volts. I lost 18 volts going down the first resistor. How many volts must I lose going through this 5 ohm? Must lose 12 volts. Oh, how many amps are there in this 5 ohm resistor then? 12 divided by 5. 2.4. How many amps were there grand total in this circuit? 3. How many amps went down this path? 2.4. How many amps must have gone down this path then? So how many amps in this first resistor here? 0.6 amps. How many in this second resistor here? Still 0.6 amps. How many in this third resistor, Jordan? Still 0.6 amps. Now I know 2 in every one of those. I got the voltage in every one of those. The top one has a voltage of I times R, 0.6 times 12, 7.2 volts. The second one has a voltage of I times R, 0.6 times 6, 3.6 volts. The third one has a voltage of I times R, 0.6 times 2, 1.2 volts. And as a quick double check, I might even add these 3 together. It better equal 12 volts, because if this one hill is 12 volts high and we can split up and meet up, these 3 hills better be 12 volts high. Are they? Double check me. 7.2, 3.6, 1.2 adds to 12. Yep. Okay. So current's going this way, yes? Current's going this way, yes? Definitely splits up, so the direction is downwards. Yes, 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 yes. Now, ready to go skiing? Here's our ski run. Did we get back to the bottom? How high is the chairlift? What did you lose going down the first hill? What's left? And that's the only, you only went down one hill and you got to the ground. How high must that hill be then? If you had 12 volts to get rid of, how high must that resistor be? So you know 12, you know the 5. If I know V and R, we used, again, this equation here, but instead of total, we just did the voltage of that resistor divided by the resistance of that resistor, and that gave us the 2.4. Is that all right? I kind of like these. To me, these are little brain teaser puzzles. I really do enjoy. Give me a circuit and let me try and solve it. And I'm a nerd, I realize, Jordan, but I kind of like these. They're kind of fun. Example 4.
How difficult would you rank this unit compared to all we've done? It seems like probably the easiest.
Not the easiest. If you do the homework, it's pretty good, though. But every year I have kids that think, because the answer to your question is every year I have some kids who during the lessons think, oh, this is really so easy, and then they try and cold turkey the test and they bomb. Don't do that. And the next 2 lessons are going to get a bit trickier. Because in the next 2 lessons, we're going to actually get a bit more realistic. We're going to say, okay, by the way, in real life, I can't remember, I think maybe someone in this class asked, in real life, the batteries also have a resistor inside. I've ignored that. We're going to look at that a bit later as well. But you know what? It fits in with our chairlift ski hill analogy pretty well. And it also explains why recharging batteries work the way they do. Example 4. What happens to the total current in this circuit as measured by the ammeter when the switch is closed? No change, increases, or decreases. Explain your answer using relevant concepts of physics. You know what? I think what we'll do is we'll solve this circuit with the switch open. Find I total. We'll solve this circuit with the switch closed. Find I total. And see what's going on. Okay? So the switch is open right now, yes? That's my high-tech drawing. Which means no electricity is flowing down that path. That's how a switch works. So mathematically, temporarily, don't write this down, I can ignore that. Which means what I really have is 2 resistors, the 20 and the 5. The 20 and the 5, are they in series or in parallel? Oh, so the mathematical equivalent with it open is a 100-volt battery. And how big a resistor? 25 ohms. What would that ammeter say total current was with it open? I can't hear. Sorry? 4. So you know what? Let's go like this. I open equals 4 amps. This is part of our proof. Now we're going to close the switch. Can you just imagine it closed? Okay, I mean, if you really want to, you can draw it in, but I'm just going to imagine it closed. How does that change? Well, now I think I have a couple of resistors in parallel. Do you see? Which two resistors are in parallel? Okay, so I'm going to go like this. 1 over R. Oh, you know what? Let's be organized. Closed. Okay. 1 over R parallel equals 1 over 10 plus 1 over 5. What's R parallel? What's the parallel equivalent of that 5 and that 10 if you replaced it with a single resistor? I don't think this one's going to work out even. Yeah, okay, 3.333333. Is that right? Yeah? I'll go 3.333 ohms. Okay, so then mathematically what I have is this. Oh, stay black, Mr. Dueck. 100 volts, 20, and 3.333. What's the total resistance now? No, what's the total resistance? Now, here's the weird part. I want you to notice this. This is actually important. This is a fundamental property of circuits, which is very counterintuitive. If I, listen close, add a resistor, let me say this again. If I add a resistor in parallel, it lowers total resistance. If I add resistance in parallel, the overall resistance goes down, which is really weird for kids to wrap their brain around. They're saying, now if I add a resistor in series, overall resistance always goes up. But if I add a resistor in parallel, even though you've added resistance, total resistance gets smaller. And you can kind of see why here with numbers. Oh, even though I've added an extra 10 ohms, it turns out this became a smaller mathematical equivalent than the 5 by itself, which meant that when you combined them, you added up with a smaller mathematical equivalent. In fact, you end up with I total here being 100 over 23.33. You know what? I'm going to go like this. Plus 20. There's the total resistance. 100 divided by that answer. And Cole, what did you say it was? 4.3?
Yeah, 4.285.
Since I'm not using this for further calculations, I'm going to be rough because I'm now going to say, comma, I closed equals 4.3 amps. And now I can tell you the answer. It turns out when you close the switch, this ammeter right here that's measuring total current, will the current no change, increase, or decrease? Turns out it increases. What does that mean? When you close the switch, this bulb would get brighter, not dimmer. This bulb would get dimmer because now it's splitting current with that bulb. Remember, power is V times I, or I squared R, or V squared over R. This one would light up for the first place because right now there's no current going through it at all. And these are some of the using principles of physics questions I can ask. Going to give you, again, lots of practice, and I got a short little video to show you too. So, number 1, 2, 3. Number 4, all number 4 wants you to do is find the that big massive thing, replace it with one single solitary resistor, and apparently you can replace it with a 4 ohm. Prove it, do the math, okay? Number 4. 5. I'm going to assign almost every question. Number 6, as a difference, they're asking you to find the chairlift height. I do notice there is one resistor where they told me 2 things. I see the 25 and the 3. That's probably going to help. Tells me it's got to be at least 75 volts high, at least. See if you can get more than that from there. 7. 8 is good. We're not going to do the air. Well, meh. We'll leave that there. So 1, 2, 3, 4, 5, 6, 7, and 8. Give me 1 second, sir.